2D, graphs can be misleading. So at this point, I want to talk about a few ways that graphs can be misleading. Let's look at the first example. Let's say that I'm a politician and I am trying to run for re-election, so I want you to understand how much I have done for you. So I present the following graph. So we're dealing with median incomes, because everybody always wants to know how they're doing financially. So I do this, so it's been a few years, so I've been in for a while, so I'm just going to say that year 2000, 2005, 2010, 2015, right? We'll even go up to 2020, what the heck? So 2020. So the years, this is a time series plot, right? I'm plotting every 5 years, and I'm going to do the median incomes. So 21,000, 22,000, and so in the year 2000, median income, 2005, median income, 2010, 2015, 2020, so there we go. So we have our time series plot for median incomes from 2000 through 2020. So I'm here to tell you that you want to re-elect me because I have caused the median incomes to increase dramatically over the time that I have been in office. Look at this, a constant upward trend. You are making more money now than you did when I came into office. This is what I have done for you. And you look at that and you go, yeah, you're right. I am making more money now than I was making then. My competitor comes in, the guy who wants my job, and says, are you kidding? Mr. Davis is a bum. Mr. Davis has done so little to help you economically. Let me show you what he has done for you. He comes in, he does his graph, and he's got 2000, 2005, 2010, 2015 and 2020, just like I had. He's got median incomes. And he's got 0, 10,000, 20,000, 30,000. And here's his data. This is what has happened with your median incomes in the time that Mr. Davis has been in office. The guy has done nothing for you. Get him out, get me in, and I'll get you some real money. Now I look at this and go, well, who's telling the truth? First of all, I've got the bigger graph, so I must be telling the truth. He had to cram his into this little bit of space. So let's take a look at it. I will tell you that both graphs are accurate. Nothing has been wrong in creating either one of these graphs. We see here that the median income started just above 21,000, and ended right about 22,000, If anything, he might have overestimated the increase. So what's the difference here? It's all about the positioning on the y-axis. Basically, I zoomed in into the 21,000 to 22,000 range. So I zoomed in on it. So you could see this dramatic increase. He's zoomed out. So his 21 to 22 range is right about there. It's just this little portion of his. So all we did was selected a different set of indices for our graphs. Mine looks really impressive, his does not. Now, if you look at it though, this is over the course of 20 years. And in 20 years, the median income went up a total of $1,000, not even. That's a $50 a year raise. That's horrible. So yes, if I zoom in on it, it looks impressive, but if you're going to be honest about it, this is giving you the right picture. Over those 20 years, the median income barely increased. Mr. Davis has been doing a horrible job to help you financially. In fact, you're probably getting poorer every year because he's there. So positioning on the y-axis is dealing with how zooming in on the y-axis can make data appear differently than it really is. So nothing wrong with the way it was done, but just the fact that it's zoomed in or not zoomed in makes it appear differently. Now there are times where you want to see this so you can see what's actually happening in there, and there are times where you want to see this so you can see the overall effect. So both perfectly valid, but something you have to watch out for. So that's called position on the y-axis or position on the vertical axis. Sometimes we don't call it the y-axis, we just call it the vertical axis. So that's positioning on the y-axis or the vertical axis. So that's the first way that graphs can be misleading. The second way that graphs can be misleading has to do with a special type of graph. And that's a pictograph. A pictograph is a graph that is made by drawing a picture. And the size of the picture relates to the data value it's representing. In 1950, the average new home construction was 1,000 square feet. In the year 2000, the average new home construction was about 2,000 square feet. Now these numbers are not exact or real. They are made up by me, but they do indicate a true trend. If you look at houses that were built in the 1950s compared to houses that were built in and around 2000, you'll see that there is a huge difference between the size of those houses. So we have these two pieces of data, and I want to use a pictograph to represent this. So what I'm going to do is I'm going to put 1950 and 2000. And then I'm going to draw a picture to represent the 1950 house. So there is my picture of my 1950 house. Now, I'm going to draw a picture to represent my 2000 house. It's twice the size, so I'm going to go twice the size. And now I have my picture for my 2000, my house in 2000. Notice that it's the same picture. We just increased the size. Do not confuse this with a bar graph where they repeat a picture to fill in the bar graph. That's just texturing or coloring in a bar graph. A pictograph is the same picture and it just gets increased or decreased to fit the data. Now that's a pretty impressive increase, doubling in size. Now here's where there's a problem. The problem comes in that something has been neglected, and that is the area principle. Pictographs and the area principle. The area principle states that the areas of the graphs must have the same, or of the pictures, must have the same ratio as the data values that they're representing. So here's our problem with this. When going from the 1950s house to the 2000s house, I doubled the height and I doubled the width to make it into this house. Essentially quadrupling the area. There's the area, there's the area. So there's 4 times as much area in this as the house from 1950, which makes it wrong. There's only supposed to be twice as much area. So my real graph should have looked like this. Or my real picture should have looked something like that black one. Notice it's not nearly as impressive looking as the blue one that's behind it. So that's one of the problems that we run into with pictographs. And to be honest, it's usually not an intentional deception. It's more a matter of ignorance. And people go, oh, well, it doubled in size, so they double both dimensions, which when you're finding area, you multiply the 2 dimensions. So when you double both dimensions, you quadruple the area. If you triple both dimensions, so if you're trying to go 3 times the size, you actually do 9 times the area. So you're really getting ridiculous in your size comparisons because the area principle is not being followed. So pictographs and the area principle, a common mistake in the graphing, misrepresents the true difference between the data values. So that's the pictographs and the area principle. Our third way that graphs can be misleading deals with 3-dimensional graphs. 3-dimensional graphs are awesome. People like to use them because they pop out of the page. You look at them and you go, wow, much more impressive than a basic flat 2-dimensional graph. So you see them a lot because they look cool. So let's get a 3-dimensional graph here. So 100, 200, 300, 400. And I can even do this here. Let's get that angle right. Okay, so thus far, I've got them. I'm going to straighten that out a little bit here. Okay, so I've got my background in place here. I'm going to draw myself a 3-dimensional graph. So first column. So I've got column A, column B, and let's get column C in here. So there we go. So now I've got A, B, and C, and you can see how this kind of pops out of the page. Even with me doing a really poor drawing on a whiteboard, instead of doing it with graphing software and everything, that kind of comes out of the page and it looks much cooler than an equivalent graph like that, right? This one looks cooler. So that's why we use three-dimensional graphs, because it helps to make the data pop out of the page. So now what we're going to do is we're going to look at these data values. Now looking at these bars, let's determine what data values we have. Well, we know this dotted line here is 100, so it looks like A is about 100. This dotted bar here is 200, so 1, 2, 3, 4. I could say that's probably about 180. And then this one here, that's 100, that's 200, so yeah, that's sitting about 150. And so we look at those and we get those data values, 100, 180, and 150. Unfortunately, all of those data values are wrong. And not by just a little bit either. Because what just happened? We're looking at this, and what are we looking at? We're actually looking from the top right-hand side. Right? I can see the top, I can see the front, and I can see the right. So we're looking from the top right-hand side. Well, what effect does that have? Well, if I'm looking from the top, well, what really happens? Okay, I'm putting my hand here, and if I put my hand down to where it's touching the bottom of the whiteboard, notice that that's about where the bottom of the whiteboard is. So I put it there where it's touching the bottom of the whiteboard. Well, I'm about halfway between the camera and the whiteboard. If I keep my hand the same height and walk over to the whiteboard, am I touching the bottom of the whiteboard? No, I'm not. I'm all the way up here. Well, why did it look like I was down at the bottom of the whiteboard when I was over here? Notice it worked right out again, right? So why is that? Well, because of perspective. You're looking from above. Since you're looking from above, you're seeing down past my hand and going behind it. Look at that, my hand is that same, I'm coming from behind. Further I go, lower I can be, and we see that there's a slope to that. In fact, I sloped that and it looked like it stayed level. But that's because of the perspective. So what happens here is, look at this distance from the back of these bars to that back line. That same distance is what we're missing here for each of these. So if we were to push this back to that back wall, we really see that instead of being 100, this is closer to maybe 120. Instead of being 180, that's closer to 200. And instead of being 150, that's closer to 170. So when we're looking at three-dimensional graphs, we have to realize that because of the perspective, the fact that we're looking from above and looking down on it, that we tend to underestimate the values represented. We see it as matching up with that, but if we push it back, since we're dealing with 3 dimensions on a 2-dimensional surface, distance is given by moving it up. So doing that would actually raise the values. So it's not necessarily that people are trying to trick you. We're just going to make a graph look cool. It looks impressive, but it has a tendency to underestimate the values. Now, there are times where you may want to do that. Maybe you want it to appear that the numbers are lower than they really are. Then by doing a 3-dimensional graph, you haven't changed the numbers, you're not lying about them, but people will automatically assume those numbers to be lower than they really are. Other times you may want to make sure that people can tell what the values are, and so they don't get tricked by it, but you still want to have it pop out of the screen, off the page. So then you do write the numbers in there so that they can tell exactly what they are. So you get the effect of three-dimensional graphs without running into that drawback of the perspective making the numbers look smaller. So 3 ways that graphs can be misleading. 1, positioning on the y-axis. So zooming in and zooming out on the y-axis make data appear to be more extreme or more subtle. 2, pictographs in the area principle. So the ratio of the areas of the pictures must be equal to the ratio of the data values they're representing. And 3, 3D graphs in perspective, that because you're looking at a 3D graph from above, it tends to underestimate the data values just by the appearance that it gives. So that's how graphs can be misleading.